All right, so homework 2 is due today, except for 2 free late days. We should be, homework 3 is on track to be out late today. And that'll just be pure OpenCL. It's like 3 problems. 4 if you want to do Mandelbrot as a warm-up. Final projects proposals due Friday. I've talked to a bunch of people. See Piazza, I posted the slides in an outline form to Piazza, the slides from last time on Piazza, so you can look through there to get an idea. There's no online form. The Piazza, the course webpage says, fill out this form. Don't worry about that. Just do the proposal this way. Just send us a one-page, 1.5-page PDF. What's that? As a team. Make sure and list everyone, and we'll get it. So just have one spokesperson send me the proposal. Okay, I want to undo some of the damage I did last time when I was trying to draw all kinds of things over on the chalkboard, and it got really ugly. So today we're talking about the halos, profiling, and then bank conflicts, which are a detail that you need to be aware of when programming a GPU, particularly if you're going to use local memory. All right, so I have a better version now of what I was trying to draw. So I want to clear it up because this will appear in a couple of problems. If any of you are doing GPU image processing where you load up a local buffer, you'll need to be able to do this. So we have an image size here that we want to process. We have an image that's 15 by 15. We're going to use a workgroup size of 4 by 4, and whatever process we have has a halo of 2 by 2. So every pixel in the green square is where we're actually computing. The red square is the information we need for the workgroup. The workgroup is limited to the green square in terms of the pixels it's going to output. And our global size then will be 16 by 16. So it'll go extend off. And that's a function of the work size being 4 by 4. All right, so we're gonna have 16 groups to cover the 15 by 15. That's the first maybe confusing part. Is it clear why we need a slight, the global size is gonna be 16 by 16 because we can't pack 4 by 4 work groups into a 15 by 15 image, right? So we're gonna have just one group, well, a few groups here that'll have a few pixels that don't do anything, all right? In terms of output. All right, there's the code here in the OpenCL. Actually, I'm just gonna go through, this is the code for the load halo example that I put in a repository. I'm gonna go through each of these lines down to here and then talk a little bit about this. I'm just gonna put them up on the screen. So if you wanna follow along in the code, that's cool. They'll be up here line by line, more or less. Okay, so the first thing we do, we get our global ID. Where is that measured from? People remember? Top left. So X and Y are our global ID. It's basically the black dot, the upper left corner of where the global ID, remember, is our position within the entire problem of this thread. So it's basically the black dot to the blue square. For that, I'm gonna talk about this blue square a lot. Right? So it's where are we relative to the image that we're processing, usually. Next step, let's get our local ID. Where's the local ID relative to? It's our workgroup ID. Anyone? All right. Where's our workgroup? The green? Top left of the green, right? So our local ID is where are we relative to the people in our same workgroup? So from the green square. All right, so now we know where we are locally and where we are globally. To load the buffer, right? The first thing we're gonna do, we're doing all this work to simplify our probably complex calculation once we have the data in the local buffer, which is going to be is the red square. So to load up the red square, we need to know where it lands in relative to the image. And that's this buff corner X, buff corner Y. And so it's our X, right? Our X minus our LX. X is our global position, right, relative to the black. Minus LX is going to subtract off our local vector, and then we subtract off the halo. So it's going to be the red corner relative to So this is where the buffer lands. We're just getting oriented because the first step is all the threads are gonna have to linearize themselves and then load up the red local memory with data to begin processing. All right, clear so far? Do you see the math that happened there? Why it works, right? Subtract off our local, and then subtract off the halo to shift it over. If we had a halo that was different in different dimensions, we'd have to separate that into the two different dimensions of the halo as well. Okay. And then we need to know where we land within the halo, right? Within the haloed local memory. So where's the blue square once we're set in the local computation, right? Because this is how we're going to access data. Once we get everything into local memory, then we're just going to operate in this local buffer, not worry about any sort of boundaries anymore, simplifying our internal code. But we need to know where we are relative to the red boundary because we need to do offset computations within the subimage that's surrounded by the red square. So we compute that just as our local and then offset by our halo, right? Our LX, LY was just from the green square. Now we just need to shift that up to the red square, so we just add the halo offset. All right? Can't tell if you're confused or, does it make sense so far? Okay.
Why did we define the corner X with the buffer corner?
The red one?
Yeah.
We need it to load data. It'll show up in the code in just a bit. We need to have it, this is all just set up. We need to get all these coordinate systems established for the next few steps, which are copying data over and then doing the processing, okay? So we need buffx, buffy for our eventual computation, right? If we had, in the slow mode that we talked about before, where we just use global coordinates for all our image computations, all our image reads, right? If we weren't doing any buffering, then we just use X and Y, right? And we'd offset them from the image pointer. We're gonna do that, except we're just gonna replace two things in our computational code. Instead of the black offset, the black image corner, we're gonna use red, because we're working in our local buffer. And our coordinates that we're going to use, instead of the global coordinates, will be buffx, buffy. The corner of the red will show up in just a bit. All right, so then, all right, we've got all our coordinate systems established. We can find out where we are relative to, note that we've got the blue square's position, that's our thread that's computing, relative to each of the important corners in this problem. And we've also got the corner, where does our buffer live in space? So we've established all the coordinates that we need. And now we're gonna get a 1D index. We're gonna temporarily suspend this 2D work group idea, right? We start this, we're doing image processing, so we have a 2D, we have a 2D global size and a 2D local size, so all our work groups are organized in 2D threads. We're gonna suspend that for a minute, just for loading data. And to do that, we need to compute a serial index, a linear index for the thread. And we take the local y times our group size, right, the width of our group size, plus the offset. And so that's a 1D index from the green square to the blue square, counting across, right, just as if we were doing image offset math that we talked about before. Except now we're gonna use it as a thread index. All right, and then, that looks like this, right? These are the thread numbers, how they're offset within our work group. We have 16 threads in this work group, 4 by 4. And so we have those as our thread indices. Now we're going to use the threads to load up the local buffer. We pretend we're a 1D work group, and the work that each thread is going to do is going to be to load its column in the local buffer. Right here. All right, I'm gonna pull up the code Doesn't fit on the slide, unfortunately. All right, it's right here. It's this loop. Oop. There. All right, it's this loop. So there's first an index check, which we'll talk about in just a sec. Now, only if I'm smaller than my buffer width. And then loop over the rows. And then we have, in this line right here, that's the offset within the buffer, right? The row times their buffer, my buffer width plus my index 1D. Right, let me go back to the picture real quick. Right, the position that I am within this red square is, index 1D is my horizontal coordinate, and whatever row I'm working on is I take the width times the row that I'm working on. Right now I'm just working on the first row. Okay.
Compared to with we have a square, because that you were saying that we interchange x and y when we compute it in coordinates by 3D.
Sorry, I don't understand the question. So we're using a buffer width here because we're, let me go back. We don't interchange the x and y. That was in this case. The interchange of x and y is the interchange of I and j indices, matrix-like indices in NumPy arrays, versus x, y coordinates as appear in images, right? So, sorry. So we're going to have each thread, based on its 1D index, load a column, or load a row, and it's going to loop through here. And then getting back to why do we need the buff corner, this is why. The corresponding point within the row is where is the buffer, that red dot, relative to the black dot in memory so that I can fetch here. And I use fetch here to deal with boundary conditions. This function fetch or macro or whatever that goes there needs to deal with boundary conditions according to what your problem is you're trying to solve, whether you're going to reflect data or store in a signal value that indicates no data or things like this for the rest of your processing. Okay, let me go back to here.
Where do we see that some of the workers won't do anything?
Right here. Right, so if the index, the 1D index, is larger than the width of our buffer with the halo, is wider than the red box, then some of the threads just don't do anything for a little while. All right. There's no, we could try to be smart and have them, loop around to the next row, but since we're talking about memory accesses and we're going to go, these are all going to go fetch a contiguous block of memory, there's no real benefit to trying to do that. It's going to serialize on access anyway.
So IDX is the index of the worker, where buff is the index of some memory.
Yes. Buffer is a pointer. Index 1D is an index for the thread index. And we're treating it right now as just a 1D problem. The 1D problem is go and fetch this row and store part of it in the buffer. Okay, so we loop over the rows. Again, a bunch of the threads just sit still, don't do anything. After it's all ready. Now we go back to 2D. We throw away index 1D. We don't need it anymore. Now we just use buff x, buff y, and can do our computation. And we just know that all the data is there in the local memory. We don't have to worry about edge effects anymore. And we know that it's fast, except for it's fast modulo the rest of the lecture.
Can you read in 2 rows at once with extra threads?
Can you read in 2 rows at once with extra threads? It doesn't help that much, usually, on GPUs, because, so the first row, red, is going to be a coalesced read, right? But we can't coalesce the second row with that first row, usually, because the offset in the full image, right, pixels that are adjacent vertically are separated by the width of the image in memory. So we could try to be smart about it. It might shave off just a little bit of time, but not that much, because it's gonna be a large coalesced read to memory, reading back 32 floats at once. And then the next one is gonna be, it's gonna have very little computation in there before it reads the next one.
Could you logically index the input image in a smart way so that like each row is a coalesced read or something like that?
Each
Global group, work group?
Each row, oh, so lay out the input image in a way such that the entire halo, not without repeating data.
Okay, that's true.
Right. So if you were going to be processing the same image many times, then possibly. Sometimes it's worth doing tricks like that where you repeat data to make the computation easier, but in this case, probably not. Was this all to do computation for the blue square? This was all computation. You mean all the crap we just went through? No, it's not just for the blue square. This is all done for every element in the work group at once. A bunch of them, right, when we were reading rows, were not doing work. But at this point, so we have a thread for every square in the green square, right? Every pixel in the green square. At this point, the local memory has the halo, and so each of those now can operate in parallel, reading data from the red buffer without worrying about boundary conditions, and they're basically helping each other, right? If we did it using just global memory reads, right? If this is if the halo is 2, then our input window is 5 by 5, right? Each pixel is going to do something with the 5 by 5 region around it. If we did that by just going to, even if each computation only read each value once, if we did that by going to global memory, then even if it were coalesced, right, very carefully done, it's going to take it's going to read each value 25 times, right? In the center, at the edge not so much, but in the center it's going to read every pixel from global memory 25 times. And there's limited caching, there's almost basically no caching there. And so that's going to be very slow. So what we're doing here is bring it into local memory, which has very good performance. And now it doesn't matter that they read each value 25 times, right? It's much faster. Oh, well, because some of them just fell off the edge of the image. You mean right here? Yeah, there are more that are also not doing anything over here. Sorry. Yeah, this extends out to all 15, also the total 16 threads. But only the first 8 can do useful work at this point. That's just so, oh, that's because that happened to be, so I just chose a pixel at the beginning.
Right. And so my question is, like, that column in our buffer is going to be relevant data that we use to.
No, it's going to be the relevant data for everything that touches, that's I see. So this column, second to last. Now I need like a laser pointer or something. So you're talking about this column, right? Anything within basically 3 pixels of this will use it. So every pixel, well, every pixel in that row, and that's it. So both those rows will use data over in this column, right? When we compute for this pixel right here, it's going to take in down to here, over to there, right? The 5 by 5 region centered on it. So that's where we get our reuse, and that's why this is beneficial, right? If we treat it if we think of not of computation, but just how many accesses to global memory have we made over the lifetime of the computation, right? For the straight to global memory approach, it's 25 times per pixel. So that would be what, 16 times 25. But if we look at this, we've only made 12 accesses to global memory, total, because they're coalesced reads, right? So that costs the same. Just reading the rows. We only went to global memory 12 times, 8 times, as opposed to 25 times 16. Well, they'd be coalesced, so 25. So.
Not because
Doesn't matter what I'm doing. I mean, I could be doing. Right, exactly, or the 5x5 window around it, right. And so that, sorry, does that answer your question? Yeah, it's just because we need a window of information. Most image processing operations are just do something within some limited space. Often, you know, no larger than 5x5 or 7x7. So the other point, I guess, is the relative to the 20, you know, going to memory 25 times versus going 8 times, is that ratio can get, depending on the size of your halo in particular, it can get much larger.
Can we look at the code? I'd like to understand where we actually start the thread and where you join them.
So you wonder where the threads start and where they join in terms of the computations. Okay.
So the piece of code we saw with the if is actually what every worker is like is running.
So everything up to this if, every thread does. Even threads that are outside the image entirely. Every thread will run every line of code here. And then if you think of it in fork join, which is not necessarily the way to think about this, there's a fork here, sort of, or there's a divergence here, it's called. This code diverges, right? Before this, everything is going just compute, 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 exactly the same thing. Yeah, every line up to here. When it gets to here, some of them have a value that puts them outside the buffer, and they basically sleep until here, right, till the end of the if statement. And the rest are within there, and they continue. So that would be just the first 8 threads.
Because their get group size 0 will be different from
Get group size is always the same. No, it's only the only thing that can be different is local ID and global ID. Those are the only values that diverge. The global size, the local size, those all have to be identical for every thread. But they diverge based on where they land within the thread group.
And the barrier is the join.
The barrier is a join. That's just because they could diverge. It's not just that they can diverge. So there's sort of enforced divergence here, right? I do an if, and some of them are outside, and so some of them stop. But you don't know how these are going to be scheduled necessarily within the group. And it's possible that some of them could actually get ahead of each other, depending on what your sort of hardware you're running on. This says, okay, now we wait for everyone to be ready, everyone to have finished writing to local memory, because that's the guarantee that then that local buffer is all the data is in place and ready for the processing. Because
So there are actually no start. Like they are all like this is a new like
there's no fork.
every worker is like
Yeah, it's not like OpenMP where you explicitly say, okay, begin a parallel section with some number of threads. You have basically all the threads that you launched at the beginning. So it happens at the beginning when you when you execute the kernel, and you say this size of a global, this global size, this local size. That's how many threads you get, and that'll be in the thousands. That could be in the 10,000s. This is the kernel code.
yeah, I see.
All right. All right, is this part clear? Yes.
So in a kernel, as you saw, there's a for loop. So that means that every thread is going to fetch the image for every row every time.
So you're talking about this, you're asking, is this for loop mean that every thread will fetch the image each time? If you look inside the for loop, it's only fetching a single pixel. So it's a loop over the height of the buffer. And each thread that passes that if test will fetch 1 pixel. Right? There's this fetch, image, and the information about the size of the image, and then 2 coordinates. And those are just 1 coordinate, or 2 components of 1 coordinate. So that thread with whatever these values will be different from thread to thread, but each one will only fetch 1 pixel per loop through the row. So going back to the picture, that is what's happening here. So that line of values is the execution of that, of the third iteration through the loop, that one line. So thread 0 fetches that pixel from the black square image and stores it in the red square buffer. Okay.
How do we make sure it's recorded in order to read?
As long as you're, so how do we make sure it's a coalesced memory read? As long as, basically, what? As long as the reads are across like this, because the image itself, the black square, is stored this way coherently in this way in memory. And so if they read it in that pattern, they'll be reading adjacent memory, right? The two values that those two threads read are next to each other in physical memory, or in the.
You said that it might be possible that one worker is going to have like the others.
It depends on the work group size. Depends how you'll specify some local. I said that some workers could be ahead of other workers. It depends on what threads can. So, for example, on NVIDIA, threads are organized into what are called warps, and there are 32 of them. But your work group could be larger. It could be 64. It could be 128. It could be in between there, and you're guaranteed that, for example, if you've got a single work group, regardless of its size, it's on one processing unit. They'll all be there on that same processing unit. But they can run independent. They run independently until they hit things like barriers. So, but they run in groups of 32. So some of them will be, if there'll be 32 of them that are running lockstep, and some other ones that may be sleeping. But that means that at least the first 32 will be read coherently. Right. That was the barrier. So we don't start the computation until the red box is full, and there's that barrier line in there that makes sure everyone is finished. And then it says, okay, now we can go. And that's why it's also a local memory fence barrier, because we only care that local memory has been written at that point. Are the gray threads bigger than 8 wasted? They're not. They're wasted in the sense that they're not doing computation right then, but since it's all memory accesses, and that's going to be serialized anyway, we couldn't necessarily get useful work out of them anyway. At that point, we're totally bandwidth limited. Can I read data? How fast can I read data from global memory into my local buffer? And that, it doesn't matter how much compute you throw at that, that's a memory width problem, right? So it's a big coalesced read, so we're basically getting maximum throughput right there at that point. So no, it doesn't, not that much. Yes?
You said that you have a barrier at the end to make sure that the entire red buffer is there. Why would you want to wait? Why would you just go start working on the already?
So why do we have a barrier? Why don't we just allow threads to begin working?
It would be like harder.
Well, the problem is, okay, suppose that my threads physically were actually just split into like 2 groups of, there were some very small groups, so 4. So this side then could fill the buffer first, right? These four threads could reach the point where they've gotten to the bottom, and so the left half of the red square would be full. Meanwhile, the other half hasn't run yet. Okay, so and if we leave out the barrier, that means that this thread could immediately start computing, right? But at that point, if it tries to read local memory, anything over here, it doesn't exist yet, it's not valid. We have to wait till everyone has filled all of the buffer, because there's going to be, at some point, some thread is going to need data that some other thread was responsible for loading. So that's why the barrier. We make sure it's entirely full because we don't know who can, when the data is valid or not. The only way we know is, have you finished writing? And that's what the barrier does. Has everyone finished writing?
I don't understand. Like I thought you said, if you load in all the entire left part, then you have that all 3, and sure, you still need like the second and the third thing to write of it, but after that happens, then you start and then.
Right. So if I could start my computation just on the left half, if I filled this left half of the buffer, then I could start any computation that only depends on the left half. Correct. That's correct, but the only way that I have to communicate the fact that the right half is finished and I can go into the right half of the computation is a barrier. I have very limited communication abilities between threads. I can say, okay, everyone wait, or that's pretty much it. I mean, I could hack up something more complicated, but it would still involve waiting, and it would turn into something very similar to a barrier. And the complexity there means that I'm going to have a lot of sort of code going in different directions. Basically, my code will get more complex trying to set up a structure to allow me to wait, and I'm going to lose my computational advantage anyway, right? I'm going to get a lot of divergent threads, some of which are waiting, some of which are not. So the simplest and really about as efficient as you can be is just wait. It won't take that long, and after that, they can just go, you know, it can be very computationally intensive after that, working just with local memory. Why don't we make the local buffer as wide as many threads that we have? So make a very long, thin buffer. That might be worth it. There's going to be there's a trade-off at some point, right? So if I made my buffer, I could make my buffer, so I've got a 2 by 2 halo, well, right, a 5 by 5 input region, and I could make the green square, I could make it a rectangle, just linear. I'm actually going to run into trouble there with having enough threads to load the full buffer. But at that point, I'm going to read every memory line 5 times, right? Because each row is going to read 2 above to 2 below. Whereas here, the number is, I think, turns out better. The amount of times I read memory is not as high. It's going to be something like, I'm going to read each memory line, or each input pixel twice, roughly, depending on how these stack. Yeah, twice, right? If you tile this with green squares and look at their overlaps, each global memory is read only twice. And it'll get better if I had a larger green square, right? Now, there's going to be very little overlap, and eventually I'll be reading the global memory only once. Right, if my green buffer covered the entire image, or my green work group covered the entire image, I would read each global memory line just once across the entire computation of all of the threads. If I had a larger buffer, which I usually would, I'd usually have something like 8 by 8 in my work group. The overlap between the halos is much smaller. Right? As I push the green square larger to cover more of the black square, the number of places where 2 red squares overlap from 2 different work groups is smaller and smaller. And so my rereads of global memory are smaller.
Try to read outside of before the local memory is initialized properly, will an error be thrown, or will OpenCL just return something crazy?
If I read before, basically if I took out the barrier, I just get random data, probably maybe zeros, probably just whatever was in the local shared memory before I started, so just not useful values.
Everything with the halos should just be read. Most things with the halos should be read just once.
So I said that everything would be read twice. In this case, if I use these sizes, 4 by 4 with a halo of 2. If you think about tiling this entire thing with green squares and then they're overlapping red squares, the red square from this to the right will cut to right about here. Actually, it's going to be 4 times. This is maybe a question for after. It's kind of specific, but basically, if my halo is large compared to my internal core, the green square, then I get a lot of repeated reads. But the idea is you usually stretch the green square out so that there isn't that much overlap between the red squares between separate work groups. Okay, ready to find out why local memory is not all it's cracked up to be? All right, GPUs have limited or no caches. I mean, the hardware, they keep on adding caches because it's still a good idea. But in general, you can think of it just uncached, and we manage the cache through local memory. That means we don't have to worry about things like, there's no caches. It's a very simple memory model. We don't have to worry about collisions in associative caches, right? Right? Yeah, I know. I was hoping he would say, why? Why is this happening? What's that?
What is a collision in associative cache?
So associative caches, I don't want to go back to it. You can watch the video. It's really painful. Associative caches, remember we have in like L2, L3, we have memory cached, and a particular memory address can only land in a limited number of places, right? It's not fully associative cache. Whenever you read a value, if there's a free space in the cache, anywhere, it can be stored there, okay? Associative can only be in a limited number of places. And if your read pattern happens to be factor with that associatively spread, then you can waste your cache, basically. Same thing can happen on GPUs. On GPUs, the on-chip, the local shared memory, it has a latency around 2 cycles. And the way they... That's CPU land. This is not associative cache, it's just you have to think about where memory is stored sometimes. But there's an easy trick to fix it. It's the same one we use for the associative cache. Latency is around 2 cycles, which is pretty good. They achieve that by basically breaking up the local memory into banks. And so memory address 0 will be stored in bank 0, and memory address 1 will be stored in bank 1, across to memory address 32 will be in bank, or 31 will be in bank 31, or 0 index. 32 will be back in 0. So basically the memory address mod 32 is which bank it lands in. Each of those banks can service a memory read at one time, but otherwise it's serialized. Okay? They can operate in parallel, so it's a lot like coalesced reads. If you read across the banks, then you get two cycle latency. If you hit the same bank with a bunch of reads in a work group, that bank will serialize them, and you'll get however many are accessing the same bank times the 2 cycles. So it's called a bank conflict. So if multiple threads in a work group access the same bank on any local memory read, then they get serialized. It's still very fast. So if you do something like this, I've got some local data and I fetch out a value and I use my local ID, right, that goes up 0, 1, 2, 3, 4, 5. And so everything is spread across the banks equally. That's perfect. This is perfectly wrong, right? If I access things 32 elements apart with the striding by that, everything's going to be in the same bank, and I'm going to go 32 times slower than I need to. Still going to be faster than global memory, but still very poor. So what does that look like? So let's say that we have an 8x8 local memory buffer. Let's assume just 16 banks so that we can draw them out easily. So this is our local data we're talking about. This is the red square after we've loaded it up. Now we're doing computation, right? So it's 8x8. So these elements in the local memory are stored in bank 0. And these are stored in bank 1. And then I don't want to put in all the colors. I mean, I made these last night, so I may have had too many Skittles. Don't tell my kids I'm stealing their candy. So bank 8, we have 16 banks. These is 8 columns across. So bank 8 lands here. And then bank 15, the last bank, lands right there. Okay, clear? 16 banks. Only going to show 5 of them, 5 of the colors. All right. How much does it cost to read this column relative to just reading one value from local memory? 2 cycles per read. How many cycles? 8. What? 4. It's 4 times higher than it needs to be. It's 8. If it's 2 cycles latency. But yeah, you're right. 4 times. Because 4 threads are going to hit the green bank, right? Bank 0 at the same time and get serialized. 4 threads are going to hit the blue bank, bank 8, and get serialized. Do you remember what we said was the fix for this, for associative memory? Just add 1 at the end. Allocate your local memory like this. I'm going to allocate an 8x9, so it's 8 rows still, 9 across. I'm going to put this extra column. I'm going to spend a little bit of local memory. I'm not going to use it at all. I'm still going to only do an 8x8 computation. In fact, I'll probably only load up those extra threads. I won't even bother loading this data either. I'll just offset it a little bit in memory. And then what happens? These are the values in bank 0 now, right? If you count across, that's 16 elements away. And then there's bank 1. and bank 2 and 8 and 15. And now what's the cost? 2, right? Perfect access. So be aware, almost always, local memory is going to go into banks of some sort. It's probably going to be 32 or 16. Make sure that, don't default to a power of 2. If you allocate just one more, your access to local memory would be a lot faster, possibly 32 times faster. Okay. Unfortunately, you have to know the hardware that you're targeting and possibly do auto-tuning. It makes it a real pain to write performant code that's portable, but it's necessary to achieve. If you're working on a particular problem with a particular piece of hardware, this is what you need to do. All right, finally, profiling. You'll have a chance to do some of this in the homework. You probably have already seen, oh, sorry, go ahead. Maybe maybe that's how your computation is shaped, right? You might be able to change that in some way, but it's often the case that you need to do something column-wise, or if you do, so it's almost never the case that you're going to be reading in the pattern where, if you're doing a computation that involves only the green squares, then you probably need to think about your computation and the memory very carefully anyway. But if you do this, you don't have to, right? You're almost always going to be reading rows or columns or something like this, and you don't have to worry, right? It could be just that maybe everyone starts with their upper left pixel, in the core, and which you would, right? So even if you're not reading the entire column, you are going to be reading the first few elements.
But if you read it row-wise,
Yeah, but you can't always operate row-wise. And you're working in a 2D, right? If you're doing image processing, you probably have a 2D work group. And they're all going to start with some pixel relative to where they are. And so you're going to have a column of workers that are all accessing the same pixel. So it's very easy to create this sort of memory access pattern in a fairly straightforward code in the way that you should be able to code. It's just that if you do code it in the most straightforward way, it's going to hit like this. Each color represents the 8-byte halo. Yeah, so this is our haloed local memory after loading from global memory. This is after we're just dealing with on-chip local memory. So yes, and then it's just each color is which of the possible banks of memory is it stored in. Basically, which element of our hardware is going to be servicing the memory request. More questions about this? In general, avoid powers of 2 for the width of your local buffer, and just bump it up by 1. All the math stays the same. You still only use the 8-by-8 region. You still only load that up. When you do that offset computation, where you figure, multiply by my buffer width, your buffer width is 9 instead of 8, and it loops around and everything's fine. You pay a little bit of local memory in terms of resources, but it speeds up your computation a great deal. So the question, why do we end up with this access pattern when we're doing 5x5 computations, right? Is that, okay. Let me go back to here. So after we've loaded in the local data, now we're ready to compute. We go back to 2D workgroup mode, and each pixel starts computing what it needs to compute. And that computation could just be like a convolution with a kernel. And so what will happen then is it'll say, okay, loop over my 5x5 region. And each pixel will start with saying, okay, let's load my upper left corner, right? Because we're in lockstep mode where everyone does everything at the same time. So this entire row says this entire column, well, the entire block, but this column says load the pixel 2 up and 2 left of me. And all of those land in this column, right? For every pixel here in this column, it lands in this column. It'll be the top 4 pixels of the buffer. If I've got a larger work group, it'll be even more. But they're all loading that at the same time, right? So at that point, I've basically generated I've generated conflicts if these only are serviced by one or two banks, right? And it's the natural way to code, right? Loop over my neighborhood in this order. It doesn't really matter what order I loop over it. I could loop, across the 5 by 5, or I could loop this way. They're still at some point all going to be accessing the same pixel relative to themselves, right? Up to and left to. And so those are all, at that point, since we're in lockstep, everyone does the same thing mode, going to all hit the bank at the same time, or hit this column at the same time. So, but if you just do that one, offset by 1, then you get this rainbow of fruit flavors in every column. You don't have to worry.
Question. So your OpenCI code
Yep.
is not taking into account bank.
Nope.
There's like
Can't do everything. Can't do everything.
Yeah, but
No, it doesn't. It doesn't.
sure, but because like the buff width is 8, right?
Yes.
So how do we do like because like now we want to have like a buffer that we use that is like of width 8, but a buffer that we declare that is like of width 9.
So you just declare the buffer width as 9. All your computations you'll just tack on, it'll be here. All your index computations will use that buffer width, right? But you don't ever actually read the data over here. You don't even have to write it. You just say, okay, make the buffer wider.
Yeah, but then it complicates the code, right? Because in the if statement,
The code will work exactly the same and just as well if you change buffer width up by 1. I'll leave it as an exercise to the reader to figure out why. But at that point, even if you do happen to load extra data, you'll load in something here, but you'll never access it. Because the green square doesn't move. The green square doesn't move, so you never read this data in the computation. All it does is it changes your offset computations within the red square, right? Once we get everything in the red square, all our image index tricks are based around the red dot. And so if it happens to go 1 wider, it's okay. Our coordinates are the same. It'll just multiply by a slightly different value there, and it should work fine. More questions about this or bank conflicts or? All right. And finally, this one is pretty profiling. In the test, the OpenCL test repository, it has some of this. Just measuring throughput, things like that. But you'll want it for some of the problems in homework 3. All you have to do really is just default to doing this. In general, you turn on profiling for your queue. If you're in production mode, maybe you don't need to do that. And when you execute some kernel, you call some kernel function, you get an event. You can call event.wait or put something else in the queue that forces you to wait. And once it's done, the nanoseconds is just the end minus the start. You'll get back from the hardware itself the timing. And that's it's pretty simple. I believe that's next time. Oh wait, no, that's this time. Oh no, that's next time. So next time we'll talk about auto tuning, kernel performance, like how do you figure out what you should use for different values for a fairly simple problem. Okay. Cool. Have fun. Enjoy the last 2 days of late days or whatever. Homework 3 will come out today. That might be like just before midnight. But I also get 2 free late days for that as well. So.